Welcome to ERC Tipsnology, and in this video I will be showing you how to calculate some DC values for a voltage divider bias using the exact analysis or the exact method. So for our circuit for today, or in this example, we will be doing the voltage divider bias, and we will be using the exact analysis, or we can also say exact method. Now for this kind of circuit, we have to take note that we will have R1 and we will have R2, and between R1 and R2 we will have our transistor. And then our emitter is connected with another resistor, which is grounded. So this is our RE, and still we have the RC. Now the source for this will be the same. We'll call it VCC, and let's say that this is 16 volts. For R1 we will say 62 kilo ohms, and for R2 we will have 9.1 kilo ohms. RC will be 3.9 kilo ohms, and RE 680 ohms, or we can say 0.68 kilo ohms. So this is our collector, this is the base, and this is the emitter. And let's say our beta is equal to 80. Now what we will do is we will find the following values, just like what we have done before. We will find the values of IB, then IC, VCE, VB, VC, and VE. We will also look for VBC, and what else? We will calculate the IC saturation, and we will get the Q point, and we will draw the load line, the DC load line. So these are the things that we will calculate. Now let's start with the IB. For the IB, we need to use a difficult formula, but I hope you understand this. This is the Thevenin's voltage minus the VBE divided by the Thevenin's resistance plus beta plus 1 multiplied to RE. Now the ETH is equal to R2 over R1 plus R2. Multiply this to VCC. For RTH, we will get the parallel of R1 and R2. So that will be R1 R2 divided by R1 plus R2. So our R2 is equal to 9.1 kilo ohms. We'll multiply it by 16 volts divided by 62 kilo ohms plus 9.1 kilo ohms. And then if you calculate this, what will we get? 9.1 multiplied by 16 volts, we will get 145.6 kilo ohms volts. And then 62 plus 9.1 equals 71.1 kilo ohms. So we cancel the kilo ohms and we will get 2.0478 volts. That's our ETH. And then here we will put 62 kilo ohms multiplied by 9.1 kilo ohms divided by 62 kilo ohms plus 9.1 kilo ohms. So if we multiply 62 multiplied by 9.1, we'll get equals to 564.2 kilo ohms. So 564.2 kilo ohms divided by 62 kilo ohms plus 9.1 kilo ohms, we will get 71.1 kilo ohms. So this is squared. So if we cancel this, we will be getting RTH equal to 564.2 divided by 71.1. We get 7.935 kilo ohms. So that will be our RTH. And this is our ETH. So now we can continue calculating for our IB. So again, the IB will be equal to ETH, which is 2.0478 minus 0.7 volts considering a silicon transistor. Our RTH is 7.935 volts, or sorry, kilo ohms. And then we add the R2 of 9.1 kilo ohms. Oh, so the RTH is 7.935 plus our beta, not 9.1, our beta is 80. 80 plus 1. So we'll be putting here 80 plus 1. And then we multiply it by RE, which is 0.68 kilo ohms. So if we subtract 2.0478 minus 0.7, we'll get 1.3478 volts. And then if we add 80 plus 1, that will be 81 multiplied to 0.68 kilo ohms. And after that, we add it to 7.935, we will get 63.015 kilo ohms. And then we divide 1.3478 divided by 63.015 kilo ohms, we will get 0.021388 milliamperes. And we can write 21.388 microamperes. Again, just put the decimal point to the right 3 times. So this will be your IB. That's it. Now that we have calculated for IB, we will now be doing the next one, which is the calculation of IC. So to calculate IC, we multiply beta to our IB. And again, in the given question, our beta is equal to 80. So what we do is we multiply 80 by the IB that we calculated before, which is 21.388 microamperes, or this is 0.021388 milliamperes. And our IC will be equal to 80 multiplied by 0.021388. It will be 1.711 milliamperes. And this will also be our ICQ. And then we will be calculating for the VCE. Now to do the VCE, we will be subtracting VCC minus IC multiplied by RC plus RE. And our VCC is equal to 16 volts minus our IC of 1.711 milliamperes multiply to 3.9K plus 0.68. So our VCC will be equal to 1.711 multiplied by the sum of 3.9.68. That would be equal to milliamperes multiplied to kilo ohms will be volts. So that will be 7.836 volts. And of course, when we subtract this from, we will get 8.16, 16362 volts. So that's our VCE. So now we have the IB, IC, and VCE. Now to continue, we will be doing the VC, VB, VE, and others. So for the calculation of VB, to calculate for VB, this will be equal to VBE plus VRE. And for VRE, this is also equal to VE, and that's equal to VCC minus VRC minus VCE. And that will be 16 volts minus ICRC minus VCE, which we calculated before. It was like, how much was that? 8.16. 8.16362 volts. And this will be 16 volts minus the IC before, which is 1.711 milliamperes. We multiply it with our RC, which is 3.9 kilo ohms. And then we subtract 8.16362 volts. We'll be getting 16 volts minus 1.711 multiplied by 3.9. We got 6.6729. 6.6729 volts minus 8.16362 volts. 16 minus 6.6729 minus 8.16362 equals 1.16348 volts. So this is our VRE, which is also our VE, which is also equal to 1.6348 volts. So that's our VRE only. So we need to continue doing this. So 0.7 plus 1.16348, this volts, then our answer will be 1.86348. So we will write here VB equals 1.86348 volts. And then after we calculate for that, we will continue doing the calculation for VC. This time VC is equal to VCE plus VRE. And VCE will be 8.16362 volts plus the VRE, which is 1.16348. Then we'll get here 9.3271 volts. This is our VC. And after we calculate for VC, we'll be doing VE. And VE is equal to 1.16348 volts because we already finished doing this here. And then after VE, we have VBC, which is equal to VB minus VC. This will be equal to, what is our VB? 0.7 volts minus the VC, which is 9.3271 volt. We will get our VBC equal to negative 7.46362 volts. And again, the negative means that the BC junction is reverse biased. Then after that, we will be calculating for the IC saturation, which is equal to VCC over RC plus RE here. And then we will be getting here 16 volts divided by 6, how much was it? 3.9 kilo ohms plus the RE, which is 0.68 kilo ohms. So we will be getting the IC saturation equals to 3.49 milliamperes. Then after that, we will be, again, like in the previous video, drawing an y-axis here. Just put IC, and then x-axis here, and just put here the VCE, and then put the DC load line. This must be the IC saturation. This will be the VCC. And we got our answer from the previous page for IC saturation. Let's open it. Okay. Here. 3.49 milliamperes. And then we have the ICQ from here. We have 1.71 milliamperes, and the VCE 8.16 volts. So we have here our VCC equals to 16 volts, and then our ICQ will be 1.711 or 1.71 milliamperes, and we have the Q point, and we have the voltage here equal to 8.16 volts. This is our VCEQ, and this will be our ICQ. There you go. This is our Q point, and this is our DC load line. So I hope you like this video. This is about the voltage divider problem, and we calculated a lot of things here, starting from the IB, IC, VCE, VC, we got it, VB, VE, VBC, IC saturation, Q point, and the DC load line. And this is the circuit for a voltage divider bias. And remember, we used the exact analysis or exact method. In the next video, I will be showing you the approximate analysis. Thank you so much. Please subscribe if you like this video, and share it. And I hope that you will like it, and watch the next video in our next tutorial. Thank you so much.